Okay, so to just recap the alpha particle scattering experiment. So Rutherford took a beam of alpha particles, which were the nucleus of a helium atom, but although he didn't know that, and shot them at a really thin sheet of gold foil. He was hoping for it to be 1 atom thick. He thought that if Thomson was right, that this beam should go through with only slight bends because of the attraction and repulsion by the positive and negative charge, the way Thomson had suggested should be in the atom. But what he found was that the majority of the beam passed straight through as if it was passing through empty space, as if absolutely nothing was in its way. And 5,000, so 1 of every 5,000 was reflected or deflected almost straight back. Okay? Now, what he concluded was that the atom must be mostly empty space then, because these alpha particles would have been scattered, but it was like they were passing through empty space. But somewhere inside the atom, there must be a large, massive, positive charge, because he knew the alpha particles were positive, and they were fairly hefty themselves, certainly bigger than an electron, right? And yet they came zooming back out as if they had encountered something that was much more positive and much more massive to repel them back out. So he called this large, massive, positive charge. He assumed it was in the middle of the atom, and he called it the nucleus. It's the first time that the word nucleus is being used here. Okay? And so he does some calculations with what comes back out, and he figures that the nucleus must be 1/10,000th the diameter of the atom. And so in class I had said if the atom is the size of this room, then the nucleus would be the size of the tip of this pen. Okay, so significantly tinier. Of course, the atom isn't the size of this room. It's fairly small, a lot smaller, so the nucleus is much smaller than this. Okay, so then his model of the atom, he envisions then this nucleus with all the positive charge and most of the mass, okay? And then he thinks, well, the electrons then must be orbiting around the nucleus, being held there by the force of attraction, the Coulomb force of attraction, right? The electrostatic force between positive and negative charges. And so as long as they're moving fast enough, remember centripetal force is mv squared over r, and so it's Fq that's applying the centripetal force here. So as long as they're moving fast enough, they'll stay in orbit. Okay, so nucleus in the center with most of the mass and all of the positive charge, the electrons orbiting around the outside, and the rest of the atom really being empty space. There are limitations to his model, unfortunately. Okay, and we mentioned them right at the end of class. The limitations, one is that if an electron is accelerating around in a circle, and whenever an electron or any charge, anything is moving in a circle, it's accelerating because it's changing direction. So if a charged particle is accelerating, James Maxwell told us back in the electromagnetism unit that it would be giving off energy. Okay, so these electrons are accelerating around the nucleus, so they must be losing energy. And if they're losing energy, it means they're losing speed. And if they're losing speed, then this side of the equation with v squared is getting tinier. And if this side is getting tinier, then the electrostatic force of attraction from the nucleus is going to win, and this electron will spiral into the nucleus, okay, and the atom will collapse. Okay, so first one, losing energy, losing speed, which is therefore losing kinetic energy. Okay, and will spiral into the nucleus. And I said losing kinetic energy. It would also be losing momentum, too, because it's losing speed. Okay? I don't know if it's a second limitation, but it's connected to the first one. It means that this atom, as the electron spiraled in, the atom would give off a continuous stream of light. The atom would give off a continuous stream of light. So we would be seeing these flashes of light as the electron was spiraling into the nucleus. A continuous, I said stream, spectrum is probably a better word. Continuous spectrum of light as it spirals into the nucleus. And then the third part of this limitation is this atom would, because of all of what I've said above, this atom would only be stable for, are you ready? 1/100,000,000th of a second. Okay, that's probably not a long enough lifespan to make this model a decent model. Okay, so it doesn't take long. This was 1911 that Rutherford did this. It doesn't take long for people to see the flaws and want to begin to improve it. And so the next person up to improve it is Niels Bohr. Okay, Niels Bohr proposes his model in 1913. Okay, Bohr's model of the atom. Now in chemistry, I think they're nice and they call it Rutherford Bohr. They're really two separate models. So Bohr's model of the atom. And I will start a separate video on this. Why? Because your test is going to end here with Rutherford, and Bohr will be on the next test. Okay?